let's take a look at position versus time graphs. And before we do that, I want to point out that when we draw a graph, we have positive and negative on that graph. Now, in reality, when we're moving around, we don't really move around in positive directions and negative directions. At least that's not how we normally think about it. We think about north, south, east, west, up, down, left, right, those kinds of directions. So when we transfer that onto a graph, just keep in mind that one direction is going to be considered positive and the opposite direction is considered negative. And in a situation, the positive direction might be considered east and the negative direction might be the opposite, west. Or positive might be north and negative might be south, or positive might be to the right, negative might be to the left, positive might be up, negative might be down. We're not going to really think about north, south, east, west, up, down, left, right when we look at these graphs, but just keep in mind that even though the graph says plus and minus, in reality that has to somehow transfer to actual directions. Okay, we're going to start out by drawing three graphs. Position versus time. The first graph is going to be sort of the simplest graph you can draw. Second graph, a little more complicated, but still not too complicated. And then the third graph, we add another little complication, but still not going crazy. So the first graph, let's take a look at that. And let's think about if we can identify what is happening to the object in a graph shaped like this. Well, from math class, you should think about this graph as being the graph of something that's constant. Here the position remains constant. Well, if your position is constant, then that means the position is not changing. Your position is staying the same. Another way to say that is you're not moving. You're staying in the same place, or this object is staying in the same place. So this graph right here, this position versus time graph, represents an object that is not moving. All right, let's take a look at the second graph. It shows that the position is always increasing, and it's always increasing at a steady rate. So it's a linear graph. And if you wanted to, you could calculate the slope of the graph, or you could find the equation of the graph. It would be of the form y equals mx plus b. So this graph is kind of nice because all that stuff you learned about lines and algebra, you could apply to this. But in terms of what's actually happening, the object is changing its position to always be more positive. The position is becoming more and more positive. So in other words, the object is moving in the positive direction for this graph. And it's moving in a consistent way at a steady pace. All right. Let's take a look at the third graph. There's more going on here. The object starts out, and it is moving as time goes by toward smaller and smaller positive positions. Another way to say that is the object is moving in the negative direction. And then it gets to a point where it's no longer moving in the negative direction. It starts to move in a more positive direction. Okay, so in the first part of the graph, the object is moving in a negative direction. And in the second part of the graph, the object is moving in a positive direction. And that point in the middle, the point separating those two regions, that's the moment when the object changes direction. So already that's a pretty big difference between the other two graphs. In this third graph, the object changes direction. Also, in this graph, we would have trouble calculating a slope. If I asked you to calculate the slope of this graph, you should probably look at me pretty funny because it's not linear. You cannot describe this graph using the equation y equals mx plus b. Let's take a look at a graph that's a little like the second one. That is linear. A linear position versus time graph. And let's think a little bit about the slope. I said that you could calculate the slope for a type of graph like this. So let's think about that. Well, slope, if you remember back to algebra, slope is the rise over run, or change in y, or change in x, or y2 minus y1 divided by x2 minus x1. No matter how you write it, it's the ratio of the change in the y variable to the change in the x variable. So if you select 2 points and you use that method, find the change in y divided by the change in x, that gives you the slope. For this particular graph, the y variable is position. So the change in your y variable is the change in position. And your x variable is in the time. Or a more natural way to say that is how much time passes. So in other words, the slope is equal to the ratio of the change in the position to the time it takes to change the position. Or said even another way, the change in the position, remember, is the displacement. So the slope is equal to the ratio of the displacement to the time that it takes to complete that displacement. That should ring a bell, because that's velocity. The slope of a position versus time graph is the velocity. And for a linear graph like this, the slope is always the same thing. You can pick any 2 points anywhere on the graph, and you will always get the same slope, which means you would always get the same velocity, which means the velocity is the same the entire time. In other words, if you have a linear position versus time graph, the velocity is always the same, so it's uniform motion. Let me repeat that. A linear position versus time graph represents uniform motion. And if I draw a different graph, like this, well, this position versus time graph is also linear. But the difference here is that the slope is now negative. So let's think about what that means. Well, the slope represents the velocity in a position versus time graph. So if the slope is negative, that means that the velocity is negative. In other words, this graph that you see right here shows you that the object is in uniform motion, but the velocity is opposite of that in the previous graph. Here it's moving in a negative direction. The velocity is negative. And if we take a look at the curved third graph that we saw at the beginning, well, I said that you wouldn't be able to calculate a single slope for this graph. And if we being velocity, the slope of a position versus time graph is the velocity, well, this graph then does not have a single velocity. The velocity is changing in this graph. But what we can do is draw something called a tangent line. And I'll explain what that means. Imagine you have 2 points on this curved graph. And let's take the 2 points and draw a line through them. All right. Now imagine making the 2 points closer together. And then you make the 2 points even closer together and draw a line through the 2 points. And you imagine taking those 2 points and putting them as close together as you can. When you do that, and you draw a line through those 2 points, that is a tangent line. Now technically a tangent line doesn't go through 2 points, because what you want to do is imagine those 2 points getting so close together that they are essentially a single point. And the line that goes through that, or those, depending on how you look at it, is the tangent line. So this may be a strange way of looking at it. Maybe you haven't looked at graphs in ways like this before, but that's how you get a tangent line. And it turns out that if you draw a tangent line through a point in a position versus time graph, the slope of that tangent line is the instantaneous velocity at that moment. So I'll show you an example. Let's draw a graph that's curved like this, similar to that third graph way back at the beginning. If I pick a point over here on the left, and I draw a tangent line through that point, the slope of that tangent line gives me the instantaneous velocity at that point. And the slope of that tangent line is negative, so the instantaneous velocity at that moment is negative. Okay, so it's moving in a negative direction over there on the left side of the page, which we knew before. That's what we said at the beginning. Now let's imagine we're down at that lowest point, and I draw a tangent line. The tangent line would look like this. It would just be a horizontal line. The slope of a horizontal line is 0, so the velocity at that moment is 0. And then if I go over on the right, and I pick a point over there, and I draw a tangent line through that point, the slope of that tangent line is positive, so the instantaneous velocity at that moment is positive. So in other words, what this is telling me is that the velocity started out negative, and then it was 0, and then it was positive. That's what the tangent lines are telling me. And that agrees with what we said at the beginning. The object was moving in a negative direction, and then it stopped and changed directions, and it started moving in a positive direction.